Meet Iris. Iris is a 95-year-old horticulturalist, and she wants help in ordering a water sprinkler to help her water her 100,000 petunias. The problem is that Iris is rather old-fashioned, and she wants to order an old-fashioned water sprinkler, one of those ones that you have to go up to and you have to tap them in order to turn them on or off. So the problem is, how big an area can she water with one of these old-fashioned water sprinklers without getting wet herself? That's the problem. So I want you to think about what kind of questions you would like to ask Iris in order to solve this question. Okay, let's look at some of the things you might want to know. First of all, Iris moves at 1 meter per second. The water sprinkler rotates at 1 radian per second. All of these water sprinklers rotate at 1 radian per second. Iris is very skinny and she's very short, so you can think of her as a point, and you can also think of the water sprinkler as a point. And lastly, the water sprinkler projects in a straight line. So let's look at all of those assumptions. There we have them. Now think of the path that Iris would take to turn off her water sprinkler. What path would she choose? So here are some possibilities. She could just go straight in. She could spiral in. Or she could go straight at the start and then spiral ridiculously at the end. Think about the path that you think is best. Now we're going to describe Iris's path with 2 variables. The first variable is r, her distance from the water sprinkler, and the second is phi, the angle from which Iris has traveled relative to her initial starting place. The unknown value that we're trying to solve for is the maximum radius of water sprinkler for which Iris does not get wet. How does Iris move in a small amount of time dt? She moves d phi around the water sprinkler, and she moves dr towards the water sprinkler. Let's try to use those in order to construct some more useful information, because those are difficult to manipulate. So what can we say about the question mark? What is that distance? Well, think of trigonometry. That question mark would be divided by r would be equal to tangent of d phi. Opposite over adjacent is equal to tangent d phi. So that means that the question mark would be equal to r d phi. Let's replace that. But for very small d phi, we are very lucky to know, and you can check this out very easily, just look at the slopes. We know that tangent d phi is actually equal to d phi for very small d phi. So that simplifies, thankfully, to r d phi. So we know r d phi, and we know that that is dr. So what is the red line? This is the distance that Iris travels in a small amount of time dt. Well, that distance is equal to, using Pythagoras, that equation. Is that useful to us? Well, not very. How to proceed? We don't know too much about distances, but we do know a number of things about speeds. So we're going to divide by dt. That gives us specifically Iris's speed. Assuming that she's going her maximum velocity 1 meter per second, we can set that equal to 1 meter per second. And that's a reasonable assumption, because if she's not going her maximum speed, you can just imagine her going her maximum speed and just doing little pirouettes in among her petunias. So it's a reasonable assumption that you can that she is going her maximum speed. And then we get this equation here. How is that going to help us? Well, let's think. Specifically, let's think about how Iris is going to get to this 1 meter radius circle and why that 1 meter radius circle is so important. Think about that. Why is that so important? Well, once she gets to that 1 meter radius circle, she's safe because she can maintain a radial velocity that is equal to or greater than the radial velocity of the water sprinkler. And probably you can argue that her best way to get to that circle is such that whenever she reaches it, the water sprinkler is just at her back. So she's just avoided getting wet whenever she reaches that 1 meter radius circle. Once she gets inside that 1 meter radius circle, then she's totally safe because then she can maintain that radial velocity greater than the water sprinklers. Let's say that she's now going to try to get, we're going to focus within the 1 meter radius circle. And let's say that she's going to try to get to that water sprinkler as fast as possible. Well, I think we're not going to prove this, but I think it's reasonable for that water sprinkler to stay at her back the whole time that she's trying to get as fast as possible to that water sprinkler. So if we assume that the water sprinkler is at Iris's back, then Iris is going to be going at the same angular velocity as the water sprinkler. And we know what that is. It's d phi dt is equal to 1 radian per second. So we can simplify this, and I'm going to get rid of the units. So now take a moment and try to find some solutions to the equation dr dt squared plus r squared is equal to 1. One solution is that dr dt is equal to 0. That means that Iris is not moving towards or away from the water sprinkler. Now that's not very interesting. It just means that Iris is going in a circle. So that doesn't help her in getting to the water sprinkler, but it is a solution of this equation. R is equal to sine t is another solution. You notice that whenever sine t becomes negative, that it looks like Iris, that the water sprinkler is not at Iris's back. This is the r is equal to cosine t solution. Notice that it's only the first part of this solution that is of interest to us. We just want to find the route that Iris should take in order to get to the water sprinkler as fast as possible, and this is it. Now I want to go back to thinking about how to get to that 1 meter radius circle, because that's what's important in order to determine R max. It's either going to be a curve or a straight line. I want you to take some time now and prove that it's a straight line. The best way to reach that 1 meter radius circle is a straight line. Prove it. Here's one proof. I'm not going to go through it, but if you're interested, pause here and go through it. There's many different proofs. This is just one. So Iris should choose a straight line, but which one? Well, we're going to define that straight line that Iris should choose by an angle phi naught. Phi naught could be equal to 0, which would mean that Iris just aims straight for the water sprinkler. We really don't want to consider phi naught is negative. That would mean that Iris is moving towards the water sprinkler in a counterclockwise direction, and I think we can pretty well figure that that's not going to be the correct solution. Phi naught, another extreme, could be that it's equal to arc cosine of 1 over R max. Convince yourself that that's true. So we know that the correct solution is going to be for Iris to choose a line that has phi naught somewhere between 0 and arc cosine 1 over R max. How are we going to move forward from this? Well, we're going to calculate the distance that Iris has to travel. And then we're going to make sure that she has enough time to travel that distance and that's going to be dependent on R max. If R max is too great, of course Iris isn't going to have enough time. So take a moment and calculate that distance that Iris has to travel in order to reach the point P on the 1 meter radius circle. The distance is given by this equation, and how much time does it take Iris to reach that point P? Well, she moves at 1 meter per second, so the time is going to be equal to the same thing. Remembering that we're dropping units here. Okay, so how much time does it take the water sprinkler to reach that point P? Well, that's going to be equal to phi naught, right? Well, not quite, because it has to go, the water sprinkler has to go around an additional whole time around the circle for it to reach there the second time. So we have to be careful here. We need to add plus 2 pi. And then we equate those two terms. So equating those and solving for R max, now we get an equation R max in terms of phi naught. Those of you who write computer programs, take a moment and write a program to discover where R max attains its maximal value. For what value of phi naught is R max maximal? That's the value we want, because that's the value that Iris wants to choose so that she waters the greatest area for her petunias. The answer is that R max attains its value when phi naught is pretty large, 82.6 degrees. That is actually the tangential extreme value. And R max at that point is equal to 7.79 meters. So let's see this solution in action, and let's watch Iris as she dodges getting wet and turns off her water sprinkler. Here she goes. So it takes her 7.725 seconds to reach the circle, and then an additional pi over 2 seconds to reach the water sprinkler, for a total of 9.3 seconds. And she's traveled 9.3 meters during that time. Iris is happy. You've helped her find her answer. But life is not over for Iris. She's 95 years old, but very soon she realizes that she can employ this newfound knowledge to attack enemy radar stations. So you can see, you can imagine flying a plane to attack this radar station without being discovered. You can see this plane is not acting too smartly because it's being detected periodically, which is the same as Iris getting wet whenever she's doing her watering of her petunias. Anyway, hope you enjoyed it. Take care. Bye-bye.